once again. So it's there. Alright guys, so last time we considered Martingale different sequence. Okay, so that was a discrete time stochastic process. Okay, just let me repeat this because that is important. Okay, so this is the next definition. So the stochastic process Y is called Martingale different sequence. Okay, Martingale difference. Okay, sequence. If the following properties hold. Okay, so this is what it was, and the first property is basically that the expectation of the absolute value of the process is equal to 0, or let's say it's finite. In most cases it's 0, but let's say it's finite. Okay, so it should be finite for all t. Okay, and the second property is, I mean, no matter what you have here, the second property is that the conditional expectation. Okay, so the conditional expectation of the process, given its past, and we have a discrete time process, so basically we'll just have a sequence here, so yt minus 1, yt minus 2, etc., etc. So this represents the past of the process is equal to 0, of course, and that is also true for all t. Alright, so this is actually what it was. Basically, this is what you have here is that the past, so given the past, okay, so this is the past of the stochastic process y at point t. Okay, so if you have point t, then of course yt minus 1, yt minus 2, etc., etc., considers the past of the process. So given the past of the process, the expectation is 0. Okay, so this is what it is basically. We had this last time. Okay, and there are certain properties that are considered in the exercise. Okay, so basically what we have here is, I mean, I'm going to discuss them, but I'm going to summarize them here. So this is the first lemma regarding certain properties of the Martingale different sequence. So let's say if y is a Martingale different sequence, Martingale difference sequence, then we have the following. Okay, so then basically also the unconditional expectation, all right, the unconditional expectation is also equal to 0. That's the first property. And the second property is that the covariance, okay, so the covariance of the process, or let's say the autocovariance, we had that, is also equal to 0 if, let's say, h is greater than 0, right? So the autocovariance is also equal to 0. Okay. Now you have to notice that the Martingale different sequence is not necessary in general, because the covariance, okay, so the covariance, I mean, we had that here, okay, so the autocovariance for, okay, so for h equals 0, we have that basically that and that the covariance of the process, right, is going to be equal to the variance. Okay, so we have the variance of the process, and the point is that the variance can depend on time. Okay, so the variance can depend on time. Okay, there are no restrictions regarding this issue. So basically what this means is that a Martingale different sequence is not stationary in general, because of course for stationarity we have to have it. The expectation doesn't depend on time, the variance doesn't depend on time, and the covariance doesn't depend on time either. Okay, so the autocovariance is not supposed to depend on time. I mean, of course the autocovariance is 0, so the process is not autocorrelated, but the variance can depend on time. Hence, a Martingale different sequence is not stationary in general. It can be stationary, but it's not necessarily the case. Okay, so hence, the stochastic process, okay, y is not stationary in general. Okay. Okay, now so what we're gonna do is we're gonna discuss a little bit the exercises that we have here, and maybe this will help you with the assignment. Okay, so the techniques that I'm using to prove these, or to prove, let's say, certain statements which are considered in the exercises, can be also applied for the assignment as well. Okay, so if you haven't finished the assignment yet, this lecture might be useful for you. Okay. Now, first off, let's start with the exercise 2.1. Okay, so basically in exercise 2.1, okay, we have a definition of a Wiener process. Okay, so let's say Wiener process, and I call this W. Okay, so what is a Wiener process? Okay, a Wiener process is a stochastic process that basically satisfies the following properties. I mean, the first property is that the Wiener process starts at 0, and you say almost surely. Okay, now if you don't know what almost surely means, you can basically say that the Wiener process starts at point 0 with probability 1. Okay, so that means, okay, so if you don't know what it is, okay, so it means that the probability that this is equal to 0 is equal to 1. Okay, so this is what it means. Okay, so almost surely, right? So this is the explanation here of that. Okay, so basically this is a constant almost surely, and this starts at point 0. Okay, so that's the first property that the stochastic process has. And the second property is that the increments are independent. Okay, so the increments of the Wiener process, okay, which are basically the differences. Okay, so you have WT and here you have WS. Okay, so these are the increments, and the increments are independent. Okay, are independent. Okay, and normal distributed, and they follow the following distribution. So you have for the increments, here you have that they are normal distributed with mean 0 and variance t minus s, of course, for t greater than s. All right, so maybe you can have that here. So this restriction, so here 0 being less than equal to s, so it could be less than t. Okay, so t is always greater than s. So s is basically the past of the process. Okay, right? So the increments are normally distributed and independent, and the variance is of course proportional to the time distance or the time lag here of the corresponding increment. Okay, so this is what the Wiener process is. Now basically we have to show that the Wiener process is not stationary here in the first part of the exercise. Okay, so this is going to be the first part, and but the increments will be stationary. Okay, so this is what we're going to show. All right, so the first statement here is that W is not stationary. Okay, and then we'll have the following statement that the increments are. Okay, so the increments of the process are. Okay, so this is going to be stationary, and I'm going to prove this by using the following method. Now, of course, we're going to prove the so-called weak sense stationary, of course, only. Okay, so what we do now is I have to show that the expectation doesn't depend on time, and of course the covariance doesn't depend on time, and the variance doesn't depend on time. Now, of course, if the increments are independent, then the process is not autocorrelated. So basically this is something that directly follows from it. but it doesn't matter. So basically what you have here is that the expectation will show what the expectation is going to be. Okay, now you cannot just simply apply that the expectation is equal to 0, because this is what we have here. You have the increment, and s would be given in that case. Okay, so the increments have the expectation 0, but the process, okay, has another expectation. Now, in order to show it, we have to apply the law of iterated expectations. Maybe remember this. Okay, so the law of iterated expectations, I'm going to write it here. So this means that the expectation of y, okay, is going to be, or is, the expectation of the conditional expectation of y. This was the law of iterated expectations. Okay, so maybe remember this. So what I'm going to do here is I'm going to look at the expectation here of the conditional expectation of yt. And the conditional expectation of yt given, let's say, y0. Okay? This is something that I can do here. Alright? Or you can also use ys if you like, but this is more general case. Now, okay? So far so good, basically. Okay? Now what you have here is, of course, what you can do is you have, of course, and you can use, of course, without ys, without loss of generality, but I'm going to use that y0, although it's 0 almost surely, but it doesn't matter. Okay, so what you can do here is that basically you can, okay, so you can take the same expectation, okay? So what I'm going to do here is I'm going to add w0 here, and I'm going to subtract here from it. So if I do this, then I basically have 0, which is added here to yt, right? So this is basically equal to 0, obviously, so it doesn't change anything, okay? Now you all know how this, I mean, you can see this here, I mean, how this is going to be treated, okay? So basically what you have is the expectation of a linear transformation of a random variable, which is going to be the linear transformation of the expectation, okay? So and since this variable is given, what you can do is you can take this out of the conditional expectation because that is given already. So basically this results in the following expression. So here you have the expectation of, and then this comes out here, so y0, right? And then plus the expectation of yt minus y0, w0, sorry. So I call this y, I'm not sure. W, I'm sorry. So w0, and then you have w0 here as the condition, okay? Now that is of course equal to 0, okay? So this expression equals 0 here, right? This expression is equal to 0. Why is that? Because obviously what you have here is that the expectation of the increment, okay, so of the difference of the two processes is going to be equal to 0. So this expectation is equal to 0, all right? So the expectation here is going to be equal to the expectation of w0 plus 0, which is going to be the expectation of w, okay? And that is also equal to 0, okay? So this is what we have here for the law of iterated expectations, okay? Now, but that does not mean that the process is stationary, basically, because we have the variance, okay? So for the variance of the process, and what I'm going to do now is I'm going to apply the law of total variance. Maybe remember this from the assignment, okay? So the law of total variance, okay? The law of total variance was as follows. So you had the variance, okay, of the expectation, okay? So this was, sorry, I'm going to use the general expression here. So the variance of y, okay, so the variance of any random variable is going to be equal to the variance of the expectation of y, okay, conditioning on another random variable x, plus the expectation of the variance of y conditioning on x. Okay, so this was the law of total variance. Now this is something that you're supposed to prove in your assignments. Okay, so all you need for that is the law of iterated expectations, as I did this for the second part. But here for calculating the variance of the Wiener process, what I'm going to do now is I'm going to use the law of total variance here. So basically what I'm going to get is going to be, and this is what you're going to see here, this is going to be the variance of the conditional expectation of wt, sorry, given w0, okay, because that's what I'm going to introduce here, plus the expectation of the conditional variance of wt given w0. So that's the rule that I'm going to apply here. I'm not sure whether or not you can see this here. Okay, I have to take a bow here, so it's quite difficult to write like this. Okay, I'm going to grab a chair next time.
There is a chair.
There is a chair. Okay, so I think I'm supposed to sit down. Okay. Because otherwise you can't read what I'm writing here. Okay. Okay. Is this clear? What I was doing here? Okay. So this refers to the law of total variance. Okay. All right. And that is part of your assignment, guys. So all you need to do for that is just to apply the law of iterated expectations, and you can apply that for the variance too. Okay. So, all right. So when you consider this, the conditional expectation, we already had the conditional expectation here. Okay. So this was the conditional expectation, right? So we don't need to consider that again. All right. But this is something that we already had. Okay. So this was the conditional expectation here, okay? And that is also what you have here all the time. So this is what you're gonna get. Okay, so for the conditional expectation, basically, which is gonna be equal to that part. Okay, so this is all what I was marking here is the conditional expectation of YT, WT, sorry. Okay, I always say YT because we have called the process is always YT. I apologize for that. Okay, so this is going to be the conditional expectation. So hence, what you're going to have here for the first part is going to be, this is going to be the variance of, and you have this here, W0 plus 0, of course, because that's going to be the conditional expectation of it. Okay, so it doesn't change. I mean, I don't have to repeat all the steps that we were doing here. So this is going to be the first part. And the second part, what you have here is expectation of the variance. Now for the expectation of the variance, what I'm going to do here is I'm going to do the same thing. So here you have the expectation of the variance, okay? So of the variance of WT, and I'm going to introduce here a zero addition, okay? So this is going to be W0 minus W0, okay? Okay, conditioning on W0. This is going to be the conditional variance, and then you have the expectation of the conditional variance of that. Right? Is this clear? Okay? You understand this? Okay? Now, of course, the variance does not depend on this additive expression because this is a constant almost surely. So basically, what you have is the variance here of the difference, and the variance here of the difference is going to be, all right. So this is, I mean, I'm going to continue here, so the variance here, I'll keep this, okay, and I'm going to change it later. Okay, so here you're going to have the expectation of the time difference because the variance does not depend on this expression, okay, so the variance basically stays the same. So here you have the expectation, okay, so here you have the expectation of the conditional variance of WT minus W0, conditioning on W0, okay. And the variance of the increment is going to be equal to t minus 0 because that is, by definition, the variance of the increment that is given here. So this is going to be t minus s, or I mean, in general case, if there's s is equal to 0, then it's going to be t minus 0. So here you're going to have the variance of yt plus 0 plus the expectation of t minus 0. This is what you're going to have. Okay, now the variance here of this expression is of course equal to 0. Right? So the variance here of that is equal to 0 because this is a constant almost surely. So what you have here is basically the expectation of t minus 0, which is equal to t. And the expectation is t, so basically that does not mean that, that means that the variance depends on time. Okay, so hence the variance of the process depends on time, and such that the process is not the process is not stationary. Okay. Okay, the Wiener process is not stationary. Okay. All right. So this is what this is what the statement was about. Okay. And now you have the increments here given. Okay, in this case, and what you can show, and maybe you can show this on your own. So on the other hand, maybe you can show, the following. So basically what you're supposed to do is, here for the increments, okay, so by defining, I'm not going to do this, so you can maybe try this on your own. Okay, so if you define the following process yt, which is going to be the increment here of the Wiener process, as you can see this here, okay, so then you need to show that the expectation of yt, okay, which is going to be the increment, obviously, okay, the variance of yt and the autocovariance, okay, the autocovariance do not depend on time, okay. So that would be the exercise for you then, okay, and you can do this similarly, what I was doing here for the process, okay. So basically you can do this as I did here for that, okay. But here you have the increments given, and of course the expectation is 0, right? But you're gonna figure out for yourself what the variance is gonna be, and you're gonna figure out what the autocovariance is gonna be. Okay, so the increments are independent, so the autocovariance is gonna be 0. And let's just see if you can do that. Okay, so this is the second part of the exercise, but I'm not gonna do this. I'm gonna leave that to you. Okay. Good. Now, second exercise, we did this already, so I'm just going to repeat the result. Okay, so this is going to be the exercise 2.2, and we have shown this already, so I'm not going to do this again. So the statement was, if a stochastic process is stationary, okay, then of course the autocorrelation, okay, with respect to h is going to be equal to the autocorrelation of the process with respect to negative h. So this is going to be the same thing. Okay, that's going to be the same. You missed something? You missed here something? Was that too quick? Too quick? Sorry. This is that one? Okay, but this is just, I mean, didn't solve the example. I just told you what you're supposed to do then to solve it. Okay? The previous one? Okay? No, just let me know if I'm too fast. Okay? Don't worry. We have time. Probably have more time than we probably need. Okay? Now we did this. Okay? We did this, so I'm not going to do this again. You can review the corresponding lectures, so I'm not going to do this, but maybe you can practice that still. Okay? Of course, so the autocovariance is symmetric and whatever. Okay? So stationarity means that the autocovariance does not depend on time, so you can use that for the correlation too. Okay? Good. Now, of course, and let's just consider exercise 2.3. So this is going to be exercise 2.3. Okay, so here we have that if, let's say, y is a Martingale difference sequence. Okay, so let y denote a Martingale difference sequence. Okay, and if that's the case, then what we have is that basically the expectation of the process is going to be equal to 0. Okay, for all t, this is going to be the first part of the example, and the autocovariance is going to be also 0. Okay, but guys, please remember, these are just necessary conditions but not sufficient conditions for a Martingale difference sequence. Okay, all right, so just because a process has an expectation of 0 and the autocovariance is 0, okay, it doesn't necessarily mean that it's going to be a Martingale difference sequence. Okay, that's another thing. All right, but if it's a Martingale difference sequence, then this is going to be the following these are going to be the consequences. Okay, now for the first part of the proof is basically easy. So what you have here is, I mean, I'm going to use, okay, so the first part is I'm going to use the law of iterated expectations. Okay, so to calculate the unconditional expectation of the random variable. So the unconditional expectation of a random variable will be equal to the expectation of the conditional expectation. Okay, so the expectation of the conditional expectation of the random variable given its past. So here I have the condition that the past of the process is given. All right, this is going to be, okay, and here this is equal to 0, obviously, right? So by definition, okay, so that was the second part of the definition of the Martingale difference sequence. So since this is equal to 0, we have that the expectation of 0 is going to be equal to 0, of course. All right, so that's the first part. Okay, again, I applied just the rule of law. I just applied the law of iterated expectations. Okay, and for the second part, we can do that quite similarly. Okay, so since the expectation is always equal to 0, so the expectation does not depend on time. So what we have here for the autocovariance, okay, so for the autocovariance of the process, we're going to have that this is going to be equal to the expectation of the product of the two. So here we have the expectation of the product of y and yt plus h. Okay, why is that? Because the expectation is of course 0. Okay, so the autocovariance is equal to expectation of the product minus the product of the expectations. Maybe you remember that. But the expectations are 0, so the product of the expectations is going to be 0. Okay, maybe it seems that you don't understand what I'm talking about, so maybe just I add this here. So the expectation of the product minus the product of the expectations. Okay, so this is what I'm talking about. But here in the previous statement, okay, I'm going to write it again. So you see it here, this better. So in the previous statement,
excuse me.
yes.
Is that an N or an H?
H for the, sorry, for the autocovariance I used H all the time. Okay, so here you have the expectation of the product minus the product of the expectations. Okay, but again, the expectations are 0. Okay, so since the expectations are 0 here, this is 0, as we've seen in the previous statement, and that is also 0 as well, all we have left is basically the expectation of the product of the two. Okay, so that was what I was talking about. I skipped that. Okay, maybe it was too fast, so that was what I was talking about, because the expectations are 0. Okay, now and to calculate that, I'm going to apply the law of iterated expectations again. So the expectation of something equals the expectation of the conditional expectation. That's what the law states. Okay, so here you have that the expectation of that is going to be equal to the expectation of the conditional expectation. The conditional expectation, I'm going to take the process, so this is going to be yt times yt plus h, given its past. And I'm going to consider the past of yt plus h, and the past of yt plus h is going to be yt, okay, then yt minus 1, etc., etc. Okay, so that's how it works. Okay, so here I close the parentheses. Okay, I'm gonna take that here a little bit to the left because I don't have much more space. Okay, so I consider this again. All right, so here you have, yes.
You said that you consider the past of yt plus h.
Yes.
But shouldn't it be yt plus h minus 1 and yt plus h minus 2?
I mean, of course, but yt is still also the part of the past, so it doesn't matter, because h is greater than 0. I mean, you're right. Okay, so it starts with yt plus h minus 1 and so forth, but I can use different past too. Okay, because it doesn't matter. So yt is also part of that. So this is going to be a subset. Okay, so since it's going to be a subset, it doesn't matter. It doesn't change anything. Okay, I mean, it's easier for the calculation because I basically I don't know in general what h might be. Okay, so I mean whatever it is. Okay, this is, I mean, in all cases this is going to be part of the past, so it doesn't matter. So I have to just take that as a condition. It doesn't change that. Okay, now since if you have that this is the condition which is given, okay, so that means that the past here is given, then of course this variable, okay, is going to be a constant, right, because it's already there, right? So we already know this. So since we already know this is going to be a constant, so what you can do is you can take that out of the expectation operator. So here you're going to have that this is going to be yt times the conditional expectation. You have yt plus h, right, given, and this is what you have, given yt, and then you have yt minus 1, and so forth. Okay, and then of course you can apply that by complete induction, basically. Then that basically that the conditional expectation here is going to be equal to the same thing, right? So this is going to be equal to yt. I mean, this is going to be 0, obviously. And you can use complete induction for that. But basically you can have, I mean, you would have that yt plus h minus 1 for the past, yt plus h minus 2, etc., etc., but it's not necessary for that. So this is going to be equal to 0. So here you have the expectation of yt times 0, which is going to be equal to 0 as well. Okay, so the process is not autocorrelated. You have it here. Okay? So if it's a Martingale different sequence, then the expectation is 0 and it's not autocorrelated. Okay? This is what you have. Okay? Now, in another exercise 2.4, okay, you have that, okay, yt is defined as epsilon t times epsilon t minus 1, and these epsilon t's are white noises. Okay, so these are white noises. Okay, so where basically epsilon t is a white noise, and not just a white noise, but let's say an independently and identically distributed white noise. Okay, so it's even a stronger argument. And suppose that we have that the expectation of the absolute value of the process is finite. Okay, so suppose that this is going to be the case, which is the case here in this part, but you don't need to look at it. I mean, we were looking at the expectation for the case where the corresponding random variable was normally distributed. So for the normal distribution, we had that the expectation of the absolute value was, I think, I don't remember, the square root of 2 divided by pi or something. I don't know, or it was something like that, the 2 divided by the square root of pi, whatever. I mean, this was part of the, I think, example 1.4 or something like that. Okay, so the expectation is at least finite. Okay, and suppose that this is the case, then, of course, and then what you have to show is that y is a Martingale different sequence. Okay. Okay. So I'm using this notation MDS for denoting Martingale different sequence. Yes. This is
what
yes.
does IID stands for?
IID stands for independently and identically distributed. Okay. So they all have the same distribution. Okay. Maybe normal, right? So most cases, I mean, this is the easiest one, normal, but it doesn't have to be normal, okay? But the distribution is the same, and they all have the same expectation, okay? So this is an independent white noise, maybe, so this process. And you have the product of epsilon t times epsilon t minus 1. And we're going to show that this process is going to be a Martingale different sequence, okay? So the first thing is to show is that the expectation is finite. Okay, so the expectation is finite, and that's the first thing to need to show. Okay, so what's going to be the expectation of the absolute value, okay, of the process? Now, of course, the expectation of the absolute value is going to be the expectation of the absolute value of the product here of the two white noises. Okay, obviously, right? So far, so good. Now, since the white noises are independent, the expectation of a product will be equal to the product of the expectations. And you're going to have that the absolute value is going to be the same, right? So to make sure that you have the absolute value which is equal, you have to have that the expectation of the absolute value of the product of the two is going to be equal to the product of the expectations of the corresponding absolute values of the two. So what I'm talking about here is that this is going to be equal to the expectation of the absolute value of the two, because the two are, I mean, the white noise is independent. Okay. Right? Do you understand this? Okay. So the white noise is independent, meaning that basically that the covariance of the two is going to be equal to 0. If the covariance is equal to 0, then the expectation of a product is equal to the product of the expectations, and this is what we have here. And we have this for the absolute value as well, okay? Because otherwise it wouldn't work. Okay? So if you take the absolute value and we calculate the expectation of the absolute value of the product, then we have to have that the expectation of the absolute value is going to be equal to the product of the expectations. Okay? Due to the independency, of course, right? This is quite obvious. Now, of course, guys, this is finite by definition, and that is finite by definition too. Okay? So since the two are finite, the product of two finite numbers is always finite. So this is going to be finite. So hence, the first property is satisfied. Okay? So the expectation of the absolute value of the process is going to be finite, which is the case here, obviously. Okay? Now for the second part, we have that basically that the covariance, okay, so the covariance of the process shall be equal to, and this is what we're supposed to do, okay? So, but before I start calculating the covariance, let me just, okay, so you can leave this, but before I start doing this, I'm going to show you that the expectation of the process is going to be also 0. Okay, so let me just add this here quickly, okay? I apologize for that, so you can leave that, but furthermore, I wanted to show something because I need this for the covariance. Okay, so I will also calculate the expectation of the process. The expectation of the process, all right, is of course equal to the expectation of the product of the two white noises. Okay, so this is going to be the product of the two white noises because that's how the process is defined. Okay, and basically the expectation of the product is going to be equal to the product of expectations. Okay. Right? Because the two are independent. Okay? I'm not sure whether or not you see this properly. Okay, so here you have the expectation of the process. Here you're going to have the expectation of the process is equal to the expectation of the product of the two. Okay, and the expectation of the product is equal to the product of expectations, again, because the process is independent, and if it's independent, then it's not autocorrelated, right? So if it's not autocorrelated, then its autocorrelate is equal to 0. Okay, now of course, this is equal to 0 by definition. We define this because the white noise has an expectation 0. So 0 times 0 is going to be equal to 0, of course, right? I need this for the covariance. So for instance, if the expectations are equal to 0, then the covariance is just going to be equal to the product or the expectation of the product of the two. Okay, so that helps me to simplify that. Okay, so that I didn't need to consider that again. Okay, you understand this? Okay, so no matter what it is, it's going to be just the expectation of the product. Okay, so what I'm going to do now here is I'm just going to plug into, we're going to plug into the definition here for that. So basically what you have and what you had is that the process is defined as the product of the two white noises here in the previous setup. Okay, so this is going to be the expectation. That was the first one. So this is going to be the white noise at point t times the white noise at point t minus 1. So this is going to be yt. And then I multiply this by yt plus h. So yt plus h is going to be the white noise at point t plus h, all right? And then the white noise at point t plus h minus 1. Okay, so this is going to be the expectation of these products here. Okay? Now, since the white noises are independent, the expectation of the product will be always equal to the product of expectations. So here you're going to have the same thing, but it's basically enough just to take out one, basically, because you can do that. You can take out any one you like. I'm going to decide here for this one. Okay. Okay. So I take this one out here from the expectation operator as follows. So here you have the expectation of the white noise. Okay, times the expectation of the remainder. Okay, so here you have the rest. Okay, why? Because of course the white noises are independent. So if they're independent, then the expectation of their product is going to be equal to product expectations, right? So basically this is equal to 0, right? So since this is equal to 0, then we're going to find that finally this is also equal to 0. So the process is not autocorrelated. Okay. This is relatively easy, but here you have an example for a Martingale difference sequence. Okay, now of course this is not autocorrelated, but it can be dependent. Okay, so here, especially in this case, it can be dependent because here you have the lag. Okay, so time is equal to 1. Okay, so at t minus 1, so the process at point t, okay, so the process at point t plus 1 is going to be equal to, and this is, you can see this here, this is going to depend on yt plus 1, sorry, not plus h, plus 1 times epsilon t. Okay, so epsilon t plus 1 times epsilon t, so you can see that the process depends on epsilon t. Okay, right, and epsilon t was also white noise, which was part of the observation at point yt as well. Okay, so again, there is no autocorrelation, but there is a dependency structure still. Okay, do you see that? Okay, so here you have this process in both of them. Okay, so there can be dependence. I'm not saying that there is. I'm saying that there can be. Okay, you have to be aware of that. Okay, so just because it's not autocorrelated doesn't mean that it's not dependent. Okay, so just because there is no linear relationship, it doesn't mean that there is no other relationship at all. Yes?
Can you maybe explain why you showed something about the autocorrelation and didn't show that E of yt?
The conditional expectation?
Yeah.
I show that too. Oh, this is what just a property that I was mentioning, but I'm going to show that too. So the expectation, the conditional expectation, right? Okay, so the conditional expectation, okay, right? So that's supposed to be equal to 0, of course, right? So given it's past, right? So here we have that this is going to be, and that's relatively easy. So here you have, all you have to have to do is you have to plug it in. So here you have epsilon t times epsilon t minus 1, okay? And the past consists of, and you have that here, so epsilon t minus 1 times epsilon t minus 2, okay? So that's the first part. And here you have epsilon t minus 2 times epsilon t minus 3, and so forth, right? So basically, epsilon t minus 1 is already known, okay? So this process is already known. So then you can take that out from the expectation operator, okay? So then you're going to have that this is going to be equal to epsilon t minus 1 times the conditional expectation of the process, okay? So here you have epsilon t minus 1 times epsilon t minus 2, and here you have epsilon t minus 2 times epsilon t minus 3, and so forth, okay? Now, since, of course, the white noises are independent, okay? So this is independent from the past, right? So here you have that the expectation, the conditional expectation is going to be also the expectation of it, okay? Because it doesn't depend on it, right? So here in this case, the expectation is going to be 0. So here you have that the conditional expectation of the process given its past is going to be also 0. That's going to be the second property. The third property is just a consequence, but I wanted to show that here too, okay? So if it's a Martingale difference sequence, then of course it's not going to be autocorrelated. All right. So given a constant, which means that you have the past, so then you have that this is a constant almost surely. So then you can take that out from the expectation operator. Okay, because it's already there, right? So which means that the conditional expectation of the process will be also equal to 0. Okay, so that was chapter 2, guys. All right. So I hope these techniques that I introduced here will help you to solve the assignment. Okay, it's not that difficult as it appears, guys. So don't be afraid. I mean, basically, I don't want to say this, but you're gonna some of the parts are gonna you're gonna find this on the internet. So it's not gonna be difficult even if you don't have any idea how it works. Okay. But try to solve this. Maybe you can try to solve this on your own first, okay? And if you run out of time, then you can use it as an excuse, whatever. Okay? Good. All right, guys. Now, if we understand everything, then we can move on. Okay? So that will continue with the lecture. We'll continue with the next topic. And the next topic will be next chapter will be about autoregressive models. Okay, so basically you have autoregressive models. Okay, this is going to be the third chapter. Okay, and I'm going to start with the first subchapter. So what is the definition of the autoregressive model? Okay, so 3.1, what is the definition of that? Okay. Now, basically, what you have for an autoregressive model is that this is a stochastic process that depends linearly on its own previous values. Okay, so an autoregressive model, okay, so an autoregressive process, okay, an autoregressive process is a process that depends linearly on its previous values, on its own previous values. Okay, so autoregressive process depends, okay, is a process, okay, process that depends linearly on its own previous values, okay? And what do I mean by that? For instance, you have an example, let's say you have a stochastic process and I call this y, and you have the process at point yt, and let's say you have, for instance, a constant, and I call the constant v, and here you have, let's say, a times yt minus 1, okay? So that means that this is, this is the previous value, okay? So this is the previous value of yt, and let's say you have a white noise here as well. Okay, so you have a white noise that kind of that is a disturbance term, okay, so that disturbs the linear relationship of the corresponding process, and which means that the linear relationship of the between the process and its previous values, okay? So this is called the so-called autoregressive model or autoregressive process of order 1, okay? So this process is the so-called autoregressive process of order 1, this one, okay? So yt is an autoregressive, or just simple y, okay? You can basically, I mean, this is, I want to achieve the consistency here. So y is an autoregressive process, okay, of order 1, okay? Why order 1, guys? Because you just have, I mean, this is the previous value, okay? Okay, so here you have the point t, and here you have the point t minus 1, and that's it. So it only depends on the previous realization. So this is a process of order 1, okay? So, and the notation for that is this. So you have y, and then you have ar, and then you open a bracket, you open parentheses, and you write 1, and you close the parentheses. So that means that you have an autoregressive process of order 1, okay? Of course, it can also depend on multiple previous values. So for instance, it can also look like this, obviously. So let's say you have a process, okay, which, okay, is in, let's say you have an autoregressive process of order 2. So if you have an autoregressive process of order 2, then obviously it looks like this. So here you have a constant b, and then you have, let's say, a1 times yt minus 1 plus a2 times yt minus 2, and then plus, suppose that you have a white noise there too. So basically this is the largest, okay? So this is the largest lag here of the process, okay? So the process depends on 2 previous realizations. So that's why you call it autoregressive process of order 2 here in this case, okay? You understand? Now, of course, this lag here can be arbitrarily large, okay? So I'm talking about the time lag, okay? So if, let's say, I'm going to define this here a little bit more precisely, and then you're going to see this here, the relation here. So let's say y is called an autoregressive process of order p, okay? If it can be written as follows, so here you have, let's say, yt, and yt is equal to, and then I will write it down here, and then I will summarize it. So here you have the constant, okay? So then you have a1 times yt minus 1 plus a2 times yt minus 2 plus etc., and then plus ap times yt minus p, and plus the disturbance term, okay, which is a white noise in this case, okay? So these constants here, okay, so these are the parameters, okay? I'm talking about these, okay? So these are the parameters, okay? This is a white noise, okay? It's necessarily the case, and you can see this here that the process depends on its previous realizations, okay? So basically you have here that yt is equal to the constant plus, and then you have a sum, okay? And the sum starts at j equals 1, and it stops at p, so you have p on the top, and then you have a j times yt minus j. So this is a, let's say, more compact notation here for that, and then you have the disturbance term. So yt, absentee, because absentee is a white noise, okay? All right, so where basically epsilon is a white noise, okay? And the mean is of course 0, and the variance of the white noise here in the general case is going to be sigma squared, okay, with the variance of the white noise is going to be equal to sigma squared at all times, okay? So this is the general definition, okay? Now these a1, a2, etc. are the coefficients, okay, or the parameters, and then you have a white noise as an error term, Okay, now there are multiple examples. Okay, so what I'm going to do now is I'm going to show you some representations of first order autoregressive models. Okay, so this is going to be the first one, and then I'm going to develop stationarity conditions. Okay, so I'm going to look whether or not or when, under which circumstances is a first order autoregressive process stationary, and then I'm going to generalize that for I'm just going to generalize stationary conditions for autoregressive models of high orders as well. Okay, so first we're going to look at representations of the first order autoregressive process. Then I'm going to develop some stationary conditions on them, and then I'm going to generalize that result on high order autoregressive models. Okay, so that's what the chapter is about. Yes, you got a question?
Is our error term always a white noise or other?
Yes, it's always a white noise. Okay, always. Okay, that's always the case. All right. Good. Now, basically, you have to notice the following thing. Okay. So, and what you also have is that the current realizations of the white noise do not depend on the past of the process. Okay. So basically, what you have is also that the current realization, so what I'm talking about this, and I'm talking about the linear relationship here. So the current realizations of the white noise do not correlate with the past of the process. Okay, so here, the covariance here, for instance, of that one is going to be equal to 0. Okay, so what you observe, let's say, I mean, if it was observable, I mean, it is not observable in the general case, but let's say it was observable. Okay, so what you observe for the disturbance term today does not depend on, or does not linearly depend on the previous realization of the process. Okay, so that's important. But it's not true the other way around. Okay, obviously, right? Because the process depends on the past. So basically, you have white noises which were in the past too. So the current observation also depends on the past of the white noise, but it's not true the other way around. Okay, so this is equal to 0, and of course, this is also equal to 0. So I mean, that is also true for any other autocorrelation or autocovariance here, to be honest. Okay, so basically you can go back to the past. Okay, 2 point t minus h, and this is going to be equal to 0, and then of course I have to add that h is greater than 0. Okay, however, okay, the process, okay, I mean, you have to be careful. Okay, because the current observation, okay, this is going to be the variance of the process, right?